Moivre's theorem. I can't tell if I'm pronouncing his name correctly. It should be something like de Moivre's theorem or de Moivre's theorem. I don't really care. But yeah, this theorem is saying that if we have this complex number in polar form, so z equals to r cis theta, then if you were to put a nth power onto z, then this is how the n applies to the right side. So it becomes r to the n, but then cis becomes n times theta. So not a very conventional, properly algebraic convention. But this is why it's called a theorem. It's because it's true, and you can algebraically prove this. And if you want to look at how it's proven, you can just look at a YouTube video simply, and it'll just show you the algebraic steps. But yes, this is the de Moivre's theorem. So let's take a look at a very, very common type of IB style question, and probably a very just common question overall across the world. So it says find all complex numbers satisfying z to the 3 equals negative 8i, and our job is to find the corresponding values of z. Okay, so z equals question mark, and as you can see, this is a polynomial to the root of 3, so there must be 3 solutions that you can find. Now, the first thing I'm going to do is structure this complex number in such a way I can use de Moivre's theorem. Right now, it's not in polar form, so we can't use it. So that's going to be the first task, to convert this negative 8i into polar form. So let's take a look. This is essentially 0 minus 8i. And if we quickly sketch an argand plane of this, it's going to be negative 8, and it's going to be right there. So this is going to be 3 pi over 2, which is the argument, and the radius is going to be 8. So therefore, 0 minus 8i can really just be represented as 8 cis 3 pi over 2, but then we can also keep rotating this over and over and get to the same spot, so I'm going to put in plus 2 pi n, just like that, where n is an integer. So we get z to the 3 equals to 8 cis 3 pi over 2 plus 2 pi n. Great. And now we're going to apply de Moivre's theorem. So I'm going to put this to the 1 over 3, put this to the 1 over 3, and times this by 1 over 3. And that is the de Moivre's theorem applied. And we get z equals to 2 cis, let's see here, pi over 2 plus 2 pi n over 3. There we go. And you can really say this is a function of n, so I'm going to input n equals to 0, 1, and 2 to find the 3 unique solutions. So when it's 0, it becomes 2 cis pi over 2, and I'm going to convert this back into the standard complex form, so it is going to be 2 cos pi over 2 plus I sin pi over 2. So this seems like it's just going to be 2i. So that is certainly a solution of z. And let's try z of 1. So it's going to be 2 cis pi over 2 plus 2 pi over 3. And I'm going to simplify this to 6, 3 pi plus 4 pi equals 2 cis 7 pi over 6. And I'm not going to go ahead and simplify this, but if you want to, you can simplify it just like that and get a standard complex number. And z2 is going to be 2 cis pi over 2 plus 4 pi over 3. So this becomes 2 cis 6, 3 pi, so that becomes 11 pi. So there you have it. Those are the 3 solutions to this problem. Just like that.